It's exam 3 for physics. This is for physics 202, S13. Ray of light strikes a thick sheet of glass at an angle of 25 with the normal. Find the angle of the ray reflected off the glass surface. I made a note of this in class. It is striking a piece of glass, but it is reflecting off of it. And so if I have an incident angle of 25 degrees and a reflected angle of also 25 degrees by the law of reflection. So the answer for number 1 is C. Dispersion of light by a prism is made possible by the phenomena of the wavelength dependence on the index of refraction. Remember we had n versus lambda, looks sort of like this. And so when light enters a prism, it doesn't have to be a triangular prism, but it can be. When light enters, comes out, it's going to come out at different angles. So the blue light will come out this way, the red light will come out that way. All right, so it splits up the colors. The following figure shows a fiber optic cable. In order for total internal reflection to occur, which of these statements has to be true about the indices of refraction? Okay, I have this light ray that's coming up along here, and then I want it to bend in that direction, that is away from the normal. So if I consider my wave fronts like this, that means it's going to have to speed up here to bend over in that direction. All right, so that means it travels faster in N2. So that means N2 is less than N1, which is A. Number 3. Consider this arrangement of mirrors. What is theta R? Oh, if this angle is 50 degrees, this angle is also 50 degrees, and that makes this angle to be 40 degrees, 90 minus 50. 120 plus 40 is 160, so that means that this angle has to be 20 degrees, so this angle is 70. So this angle theta R is also 70 degrees, so that's B. Organize these radiations in the type of lowest to highest energy. All right, the lowest is microwaves, next is infrared, visible next, and then gamma rays. Microwaves are just a form of radio waves, a little shorter wavelength. So it's A. Which of these statements best characterize the indices of refraction? So if I consider my wave fronts, in order to bend this direction, it has to slow down here so it can turn here. So it travels slower in N2. That means that N2 is bigger than N1. So that's going to be A. An image is found to have a negative image distance. What best describes this image? Negative image distance means that it's virtual. All right. It's not inverted. In fact, another correct answer would be that it's upright. If it's at least if the object was upright, because remember magnification is negative Q over P. So if this is negative, that means the magnification is positive, which would make it upright. Smaller than object could be either way. Imaginary doesn't make any sense. Mirages are caused by which of these phenomena? Mirages, remember, look like reflection, but they're actually caused by refraction. This figure shows the configuration of an object lens and an image. What kind of lens has produced this image? This lens that produced this has been a convex lens. If I draw my rays, it looks like this, parallel to the axis through the focal point, parallel to the axis. All right, so that is a convex lens, B. You stand 2 feet away from a plane mirror. How far is it to your image? If I'm standing 2 feet from a mirror, that means it's another 2 feet to my image. So that's from you to your image is 4 feet. A. Which of the following best describes the image of a concave mirror when the object's distance from the mirror is less than the focal point distance? All right, so the object is inside the focal point for a concave mirror. It's going to look like this. This is my object. That means that my image is virtual, bigger, and upright. This is like the makeup mirror when you, or your shaving mirror or whatever, when you hold it up close and your face looks real big. So that is a virtual, upright, and magnification greater than 1. C. When the reflection of an object is seen in a convex mirror, the image, remember convex mirrors like this, this is my object, they're always virtual, they're always smaller, and they're always upright. So A. It's never enlarged, it's never real, and it can only be virtual. Can't be real. If atmospheric refraction did not occur, how would the apparent time of sunset be changed? Sunset would occur earlier. Remember, if we have the Earth right here, here you are, and the sun's over here, you have light rays that come, but they're blocked by the Earth. but because of the refraction of the atmosphere, it bends around. And so sunset actually occurs later for you. The sunset that you observe occurs later than the actual dropping of the sun below the horizon. So if you didn't have the atmosphere there, the sunset would occur earlier than it does now, and you'd be dead. All right, which of the following effects is a result of the fact that the index of refraction of glass will vary with wavelength? Of these, that would be chromatic aberration, C. Let's see, this was A. Remember, I have light rays that come in of a certain color. They focus at a particular point. When I have light rays that come in of a different color, because the index of refraction changes with wavelength, those rays focus at a different point. Reducing the lens aperture size is a scheme one can use to reduce the occurrence of which of the following effects. That would be spherical aberration. You have rays that come in here. They focus at a particular point. And then you have rays that come in the center of the lens, and they focus at a particular point. But if you mask out a portion of the lens, it gets rid of this part of the image and reduces that effect, that aberration. All right, find the final image position and magnification for this two-lens system. All right, so this is P1. Our first step is just to find Q1. Q1 is 1 over F1 minus 1 over P1. That's 3 over 30 minus 1 over 30. It's 15 centimeters. So my image, oh, and then the magnification M1, let's go ahead and find it, is negative Q1 over P1. That's negative 15 over 30. Negative 1/2. So Q1 looks like it's going to be right here. It's going to be half the original size. This is Q1. It's going to be 15 centimeters. There's a remaining 5 centimeters. That's going to be our P2. P2 is equal to 5 centimeters. And so now we'll use that to find Q2. So Q2 is going to be 1 over F2 minus 1 over P2. That's 1 over 10 minus 1 over 5. Negative 1 over 10 to the negative 1. That's negative 10 centimeters. And then my magnification is positive 2. All right, so because it occurs at negative 10 centimeters, that means that the second image, which I'm going to draw here in red, occurs right here. It's twice the size of this first image because the magnification was positive 2, and it still remains inverted. All right, so the final image position then is 10 centimeters to the left of lens 2. And then I also wanted to know the magnification. The total magnification is M1, M2. That's negative 1. Right. For what it's worth, this is a virtual image, not a real image. And I know that it's virtual because Q2 comes out to be negative. So it's a virtual image. It can be seen but not projected onto a screen. Person stands 4 meters in front of a convex mirror, so P is equal to 4 meters. The center of the curvature is 2 meters, so that tells me that the focal length is half that, C over 2. So the focal length for this convex mirror is 1 meter, but a convex mirror has a negative focal length. I want to know what is the magnification. Magnification is negative Q over P. So first I need to find Q. It's 1 over negative 1. what's that, -0.8, 4/4, -5/4. All right, so Q is -0.8, and then I can find my magnification is -0.8 over P, which is 4. So that's equal to +0.2. Draw 3 rays for this lens, show the location of the image. So my first ray will be parallel to the axis, and then it goes through the focal point. Remember, this is a diverging lens, so it does this funky thing where it goes up, such that if you traced it back, it would go through the focal point. And I went and traced it back because this is one of my virtual rays. That is the refracted ray traced back, and my image will lie somewhere along that ray. This was rule number 1, by the way, from our rules. Number 2 is through the focal point and then parallel to the axis. So I draw it up to the lens such that if I were to trace it forward, it would go through the focal point and then parallel to the axis. Go ahead and trace that ray back. I know it has to be a virtual ray because rays number 1 and 2 diverge, or it has to be a virtual image. So I can go ahead and draw my image in right here. It's going to be right here. And then I can draw my third ray, rule number 3, just straight through the center of the lens. Looks like that. All right, this is a virtual image. It's upright and it's smaller. And I think this is the last one. No, there's 2 more. What must be theta naught for total internal reflection to occur in this fiber optic cable? All right, couple steps to this. Theta C. I first need to find what is the critical angle right here. We had a homework problem basically identical to this. I'm going to have N1 sine theta C equals N2 sine of 90. That's the critical angle that will cause the ray to go at 90 degrees to the normal. So theta C is the inverse sine of N2 over N1. It's 1.2 over 1.3. It's 0.92. Oh, I'm sorry, the inverse sine of that. 67 degrees. So that means this angle has to be at least 67 degrees. That means that this angle has to be 90 minus 67, which is, what's that, 23 degrees. All right, so now we do another refraction. We're looking at this interface. I'm going to sort of blow it up in a simpler diagram. This is theta naught. And this angle is 23 degrees. This is n equal 1, n equal, what was that n? 1.3. So I'm going to have 1 sine theta naught. Theta naught is the angle that I want. Is a 1.3 sine of 23. So theta naught is just 1.3, or the inverse sine of 1.3. I get 31 degrees. A dentist uses a mirror to examine a tooth that is 1 centimeter in front of the mirror, so P is 1 centimeter. The image of the tooth is formed 10 centimeters behind the mirror, so Q is negative 10 centimeters. Determine the mirror's radius of curvature. First, I'm going to find the focal length. The center of curvature will be twice that focal length. So let's go ahead and find the focal length in the mirror equation. 1 over 1 minus 1 over 10. 10 ninths. 1.11 centimeters. Determine the and so the center of curvature is twice that, or 2.22 centimeters. And in part B, you want to know the magnification of the image. That's going to be negative Q over P. It's negative 10. So that tooth looks 10 times as big as it actually is. It's a pretty good mirror, actually. There's the multiple choice.